Okay, the purpose of this video here in lesson 3 is to take you through this thought process of building this notebook. The first section here that you kind of come to when you pull up the notebook is how the course is related back to the modeling process and the models that we'll use throughout the course. So I'll let you kind of read through that. But the first model here we talk about is regression, and so we'll start there, and then you can see maybe. We have a data set and it's a clean data set. I will not explore it here in this video or in this notebook. I'll let you do that. You're definitely invited to try to do that on your own, explore, do some of the things that we've done in the previous couple lessons. The data is clean and it's ready for analysis, so we don't have to do any data wrangling / munging on it. And this collab stuff, I really wouldn't worry about. I'm not going to ask you guys to do that, but it's there just so you can kind of see how I can hook it up to my Google Drive if I really want to. All right, so I call it DF, data frame. That's a very common thing to do. And so I'll read in. So you have to download the data set, the auto.csv, put it in somewhere in your computer where you can get to it. Mine, obviously, I had to come up twice and then go to data sets and then eventually find it. And then when it pops out, it comes up and it has this look to it, and I didn't like the fact that they had it. It had a number assigned for each vehicle. It looks like there's 397 vehicles, and so I wanted to get rid of this row. And so remember how to drop a column, not row, column. I wanted to drop this column, and so I dropped it, and then I reprinted it, and you can kind of see what happened. So that's what we have. Another way to do. There's other ways to do that. I just didn't. This is how I attacked the problem. Okay, so So remember what we're trying to do. If you kind of go up here, it says, hey, we want to do something where I'm trying to predict the car's miles per gallon, right? So I did a little preliminary, not a whole lot of looking around, exploring the data. The one thing that I did do is a little correlation map, heat map. And I found out that when you look at miles per gallon, that weight has a negative 0.83. That is not necessarily the only thing you want to look at, but I don't know. I just kind of pulled that out and said, you know what, then I'll just, and it made a little sense to me that more something weighs, the less miles per gallon you'll get. So I decided to do a little scatter plot, and it kind of looks like that. So what we want is a linear regression or a linear model, right? So that's the idea behind this lesson, is I want some kind of linear model that will fit, /fit all these data points. And obviously they can't go through all of the data points, and so we want the one that fits this data the best. A little bit about notation before we get too far. Y is the response variable, and you can kind of see it here. It's just, whatever the values are that are on the y-axis here. In this case, we only have one predictor variable, right? I'm using miles per gallon. So I would have, this matrix would be cut here. I would only have one predictor variable, right? So this whole column here would be a bunch of weights, right? So this would be weight of car 1. This would be the weight of car 2. Next one would be a weight of car 3. This would be the weight of the very last one. I forget how many we had. So, and then you'd have a column of ones, and so that would be a matrix of numbers. And we're going to find out, hopefully, very quickly here, why we set it up this way. Now, a little bit about notation. The sub, like the sub 1, XM1. That is the predictor variable, right? So X1 would be, if I had an X2, that would be the second predictor variable, and X3 would be the third one, XP. So what I'm saying is I have P predictors in this model. In this superscript, so that's a subscript. So if I had a superscript with the parentheses around it, that's the number of data points that we have. So right, so the superscript 1 within parentheses would be the first data point, and the superscript 2 would be the second data point, and the nth data point, and so on and so forth. So I'm saying I have n data points with p predictors, and so we'll try to use that throughout the semester so that we don't get confused or whatever. Sometimes you'll see m by n because of linear algebra. You have m rows by n matrices. In this class, it'll be an n rows by p. Actually, it'll be an n by p plus 1, right? Because I have this extra column here. Okay, and so you guys can read through here, right? So I have x. It could possibly be more than 1. In this case, it would be a 1, x1. and so on and so forth. So in the ith training example would be that one. So you can kind of see the picture here. You can follow through that piece. I'm not going to go too much into detail. You guys can read and ask questions in class if you want to. How do we represent the function then? So it's so now I have parameters. So I haven't really talked about that yet, right? No, I haven't talked about. Oh, and I did. So I had this beta 0 plus beta 1. I don't know what the best beta 0 and the best beta 1 and kind of goes through these points the best. But that's the idea of this class, is that we can come up and sort of try to figure out how we're going to measure what beta 0 and what beta 1 does, right? So what we're allowing is having this, I have a function, this g of x, with respect to some beta, and I could put a vector sign over there because it's beta 0 and beta 1. Let me see. No, we didn't talk about that there. So this could be a vector symbol over the top. I have beta 0 and beta 1. And if I have a beta 0 and beta 1, then I can produce these y hats. And it assumes some kind of linear relationship. And so this y hat is the estimated response given some beta 0 and beta 1 and the x value. Okay, so this next piece is just simply, hey, let's just show you what it looks like, right? So obviously, if I give you different beta 0 and beta 1s, then you're going to produce a different line. And so you can kind of see, and I could have made this a line if we really wanted to, but I just wanted to throw some dots out there. You can kind of see. So if I put in a particular point, you put it into the function here, you're going to get out that value. So if this were my line 1.5 plus 0x, obviously it doesn't matter what happens to x. It just kind of goes through the point, or I'm sorry, the y value 1.5, right? So it's always 1.5. So here my function value is half 0.5 times whatever x is. So at 1, I should be at 0.5, which I am. 2, I should be at 1, and so on and so forth. And here it's 1 plus 0.5, right? So at 1, I should be at, let's see, 0.5. So 1 plus 0.5, yes, so 1.5, this is good. So again, all I did was I took this line and pushed it up some, right? So 0.5 is my slope. I pushed it up by 1. It might not look like it, but it's probably has to do with the scaling on here. All right, choosing the correct beta 0 and beta 1. So that's the whole purpose of this lesson. We talk about choosing a cost function or a loss function. So the loss function here is going to be this function where all I do is I take 1 over 2 times n. Remember what n is, the number of data points that we have. And then we're going to sum all of those in this function. Give me a beta 0 and beta 1, right? In this case, a beta 0 and beta 1, and the x value. And I'm going to put it in here. And I'm going to, so that'll give me y hat, basically. And then I'm subtract the difference between them and square it, right? So why do I square it? Because I don't want it to negatives to cancel out with the positives, right? So it could be the absolute. So you'll see up here we talk about absolute value. You could do that as well, but it just doesn't lean itself to calculus. So we're going to use calculus to find the derivative here in a second. Okay, so that I get that is going to be my cost function, and then we give you a sort of a simple, I just kind of made up these data points. They don't mean anything, and we plot them out here. And in this particular case, we're gonna just do one. So I'm gonna just do one of these functions. I'm sorry, one of these parameters. I'm gonna set beta 0 equal to 0, and we're gonna solve for beta 1. So in other words, it's gonna go through 0, 0. Here it's gonna go through the origin, and then I just want to find beta, whatever beta 1 is. It's gonna fit these points as best as possible. You can kind of see what that is given that loss function. So, okay, so now we're just gonna give you examples. Right now I'm not finding it, but I'm going to give you an example, right? So if I chose beta 1 equal 0.5, then that would be my line. Those would be my 3 points. And if you look down this one, then you got the first data point, xi is 1, yi is 0.5, right? So 1.5 is right there. And then given that beta 1 is equal to 0.5, 0.5 times x is 0.5, subtract those two and you get 0, right? So for this first point here, the loss function is 0. Why? Because it goes right over top of that point. You look at the second point here. I guess I should have put this thing maybe right underneath here. Yeah, yeah. Anyway, so I don't have to keep scrolling back and forth. But you get the idea. The second point, x is 2, y is 3. If you put 2 into the function, then you'll get 2 times 0.5, which is 1. Subtract these 2 is 2. Square it is 4. So 4 and 1. And if you added 4, and so if you add up all these losses, which is what you're doing with the summation sign, all of these losses squared, then you get 5, right? And then I get to divide by 2 over n. In this case, I got 3, so 5, 6. So if I came down here, sum of the loss divided by, basically my loss function is 0.83, it's 5 over 6. The second one would be 2.25 on top, and then divided by 6, right? Because it's not going to change. 2 times 3 is always going to be equal to 6. And then this last one would be 9 plus 1 would be 10 on top, and 1.666. Okay, so if we did that, then the best one of these three that we sort of arbitrarily selected is what? Well, you just pick the one that's the lowest, right? So it's 0.375. So obviously, that's not going to be the, well, I shouldn't say obviously. So it's not very obvious what the answer is, but what we have to do is we have to change beta 1 in order to make this number smaller and smaller and smaller. And the question is, well, how do you do that? So, so what I'm going to talk about just for a second is single variable optimization. And you can kind of see what's going on there. So I create this G function. Well, all it has is this beta 1, and the cost is, it just adds up all the error in there, and we get, let's see, I put in cost as 0. So again, it's just, all this thing is doing is exactly what we did on this table up here. So you can kind of go through and check out what it's doing. It's pretty straightforward. We're going to redo this here in a second and use Python's capability, or I'm sorry, NumPy's capability to do this very quickly. You'll see here in a second. But I just wanted to print out these costs to the using the data. I don't see. Oh, the data here is are these 3 points, right? So data is just these 3 points. Let's see here, and then beta is equal to NumPy. Oh, so now what I want to do is I want to let's graph this squared loss function versus beta 1, right? So now I can, what I can do is I can create a bunch of different beta 1s using NumPy's capability here, and then we can create a beta. What is the loss or what is the cost for each one of those betas? And that's all we're doing here. So we're kind of doing the same thing here, except I'm not using the arbitrary 0.5, 1, and 1.5. I'm using the betas in between 0 and 1.5 and substituting those in, right? So for B and beta, so look at what I did. I did 100 betas in between 0 and 0.5. That's what linspace does. And then for each one of those, I substituted. I did the exact same thing I did up here, with the 0 being my beta 0 and B being in my beta 1, B being all the betas that are in there. And then I just simply substituted into this function up here, and it gives me what's happening, right? So you can kind of see the cost, the loss/cost function for the data given the model, right? So you can see what happens. And obviously 1 is not the lowest, but 1 is pretty small, right? So the lowest would be somewhere in here. Now, you could estimate it. I mean, you could kind of get a sense of where the smallest is and maybe come down and say, hey, I want one that's about 0.89. I don't know. Maybe there's a better technique, right? So the next thing is, well, there is a better technique. There's this thing called steepest gradient descent or steepest descent for a single variable. So what does that look like? If you think about it to your calculus class, all we're going to do is if I'm on the left-hand side of the small part, right? What is my derivative? We'll check it out. So my derivative is always going to be negative over here, and it's always going to be positive on this side. And what happens as we get closer and closer and closer to this point that I don't know? Well, the derivatives are going to get smaller and smaller and smaller, right? Because we know when we're here that the derivative is going to be 0. So it's going to be a small negative number, so if I were to draw the little slope here, it'd be a small green, right? So it'd be, the slope would be very, very small. And we know when we get right at the point that we want to be at, that it's going to be 0, right? So that's how I'm going to look for that particular number. So all I'm doing, so this is the sort of the process here. So I want my old beta, So if I put in some value for beta, so let's suppose I put in it right here. If I put it in here, this is going to be a positive. So I know I need to go negative. I need to move in the negative direction. And that's why that minus is there. So give me the derivative, multiply it by, now why do I multiply by a small step size? Well, think about this for a second. If this is a huge number here and I just multiply and I go into a huge negative, it's going to jump way over here somewhere. And then I'm going to put that in. It's going to be even bigger and it's going to keep jumping. So it's going to diverge. And maybe, matter of fact, we'll do this in class. We will show you how if you don't make this really, really small, that this thing will certainly diverge and it'll keep jumping back and forth and going a little nuts. You want alpha, you want this little step size. How big of a step am I taking? I want it to be very, very small. But if I'm on this side, I always want to move in this direction. And if I'm on this side, I always want to move on that direction. So, okay, so what I did was I calculated, and again in class we'll talk about where this function comes from. This is my new cost function. I called it J. You can see that it's a lot cleaner. Hopefully you think it is a lot cleaner than this cost function that was up here. So I got J, I got DJ. So we're going to talk about this again in class tomorrow. And then test function. So I just test this thing out and you can kind of see what happens. I think alpha is 0.5, 0.1. Look, it works with 0.1 for this small little bitty 3 little, because things are small here, 0.1 will work. But I tell you that when we get to the ones down low, that won't necessarily work. So you can see that 0.88 works for that, and then we could graph. Oh, I didn't graph it. Well, I tell you what, we'll graph this sucker tomorrow just to show you on these 3 little knucklehead points here. Where'd they go? These 3 little points here. That 0.88 with beta 0 equal to 0 and beta 1 equal to 0.88 something, that's the best line. Well, I don't know if we need to graph that, but we can. And then what we do in this notebook is we say, all right, well, I just sort of assumed that V0 is equal to 60. I don't know what the right answer is. We're going to do that later on, but we're going to assume some value for beta 0, and then we're going to solve for the best beta 1 for that beta 0. And then here you see that I assigned X equals the weight, Y is equal to MPG, and then assign some arbitrary value for beta, and then we just kind of we printed that. Just testing the cost and just to make sure that it's working still, and then we implement the steepest descent, and you can see that right there is the value for beta 1, and then we plot it. So this is the goal of our thing today, was to get a line through all of those data points. Now, is this the best line? Probably not. I don't think beta 0 equals 60 could possibly be the best line, but we'll talk about multivariable gradient descent later on. Well, and I say gradient descent, but really it's in this case it's just the derivative descent, right? Because we haven't really taken a gradient because we only have a single variable right now. Okay, well that's all we got. I apologize. It did take 20 minutes, but you guys can fast forward through stuff if you need to. All right.